Welcome back, everyone. Our next talk is called Role of the Cloud in Autonomous Vehicle Vision Processing, a view from the edge. So I think we're going to hear a little bit about what's done in the cloud, what's done on the edge, what's done in the sensors, what kind of sensors do we have, and why. Our speaker is Ali Ors, who's the Director of Automotive, Microcontrollers, and Processors at NXP. In addition to getting an engineering degree from Carleton University, he also worked at Cognivue Corp. Please welcome Ali.
Thanks, Al. Thank you. Thank you, everyone. Yeah, just to recap slightly, with NXP Semiconductors, I'm currently the Director of AI Strategy and Strategic Partnerships for our Automotive product group, and looking at all the signal processors for radar, LiDAR, cameras, specifically vision, and of course the central compute that we do. So today I'm going to touch on where cloud processing can be applied in autonomous vehicles, where it is being used, and how we see that progressing. Just to quickly touch on the basic autonomous vehicle system as we know it. We apply it to the sense, think, act model, and the sense model of this is where we have all the sensor inputs. So even from the lowly ultrasonic to the usual suspects of LiDAR, radar, camera, and the telematics sensors coming in to what we label as a perception module. This creating a view of the environment of the vehicle, and then feeding into the thought module, the think module that uses map data to localize where the car is within a given map, and it gives it information about what is surrounding it, and this information then used in the path planner to actually take the car from point A to point B as you would need in an autonomous setup. All of this then circled by what we call a safety channel. So the path planner takes care of a long-term trajectory, whereas the safety channel looks at the immediate implications of that path planner's output and decides if the path planner is making a safe decision on how to move the car forward, backwards, etc. And as long as it's safe, then you have the actuation modules coming in with your steering, your transmission, acceleration, deceleration, and braking, etc. So the data around the car is not static, it's a constantly dynamic model, and you need to be able to accurately sense to safely respond to your surroundings. I wanted to touch on typical sensor topologies in the automotive sense, in the automotive context, of what we as NXP see as a likely, from least likely to most likely topology of how these various different sensors and their modalities and constellations would likely be used in automotive setups. So you're starting from a model that's mostly used for ADAS, for low count of sensors type of applications, where you have a very distributed model with no central fusion unit. You have a lot of intelligence at the edge. We see this as least likely to move forward in the designs of future cars, especially when you get into autonomy. But it does create a good solution for lower bandwidth utilization, because there's no fused data to be exchanged. In a sense, all the data is consumed at the edge where you're doing the processing, be it vision or radar, and you're doing it with intelligent sensors. You don't have compute centrally located. This is good for for reducing bandwidth that you're carrying across the car, but you have an increased sensor cost with your intelligent sensors. More likely, moving forward, especially for smaller OEMs or more innovative OEMs, is the centralized view of your sensors. So where you have a very large central compute brain taking in all the data. So this is the best theoretical use of data fusion, because you're getting all of the raw data into that central compute unit. But of course, you have a very large bandwidth requirements of carrying the data into the central compute. And it's also not a trend we're seeing from the sensor vendors themselves, creating simple sensors. Everybody's trying to add more intelligence at their product level. It might be likely, especially for autonomy. We're seeing some OEMs move into this realm. But we see as most likely is the hybrid model, where you have some intelligence at the edge and a smaller or medium-sized brain, central compute brain, centrally, using some of the data that is aggregated at the edge and then bringing that in centrally. So this is where you have the pros and cons, and it's the most flexible and scalable model. You're managing your cost of data movement with your cost of data processing as well. And it leverages the smart sensing as well as local aggregation. Now, if we look at what cloud computing typically is used for and how in non-automotive applications as well, where you would have the cloud is for offloading processing, so the three pillars, offloading processing. You would use it for updating applications for maintenance purposes or feature addition purposes. And you would have it for storage and data logging type of applications. This is where the cloud is typically utilized. If we apply that same model to the autonomous vehicle side, we're seeing that one of those pillars, the offloading of processing, is really not applicable for an AV scenario because autonomy and safety-critical driving decisions are real-time problems. You cannot have it reliant on a cloud-based setup where the connectivity might be potentially unreliable, might have varying latencies for connections, and the infrastructure might exhibit internode problems. So you cannot have a real-time safety-critical process relying on its processing to be somewhere else. So we believe that the offloading of the processing from a cloud perspective is not likely to happen in an AV setup. But the other two applications of using the cloud for an update functionality, for feature maintenance, or using it for storage and data logging is still valid, and I'll be going through some examples of that. So one example that we can touch on is if you have a path planner failure. So we touched on how in the Think module, your path planner is looking at a longer range trajectory plan for you, and the safety channel is actually doing a more immediate analysis of where the car is moving, and if this is a safe movement for the car. If there's a mismatch between these two parameters, so that the path planner is actually moving the car into an unsafe zone and the safety channel kicks in and tries to bring the car to a stop or to a safe harbor, then that is an event that needs to be logged and communicated. So the act of the communication and the act of communicating up to the cloud is one of these examples for cloud use in AV space. Another model is the use of maps. So maps are extremely essential for high-level autonomy. You have a lot of your localization based on maps, being able to, with vision systems, being able to look at landmarks that are identified in the map to locate yourself within that map to see where you are in the world, and also maintain a certain position dictated to you. So even within a lane, AVs have a certain corridor with 10 to 20 centimeter resolution that they need to maintain to. We'll get into that corridor's implications later on, but if the landmarks that are provided in the map are not matching what your sensors are picking up, what especially your vision sensor is picking up, then you have the AV potentially not being able to locate itself, not localize itself, and have a disengagement. And the disengagement is a measure that a lot of AV platforms are using as a measurement of the robustness of their solution and the ability of it to handle all general purpose applications. And you don't want disengagements. As the saying goes, if you hear hoofbeats, think horses, not zebras. But sometimes you have to think zebra. So this is an example of if your perception piece is not actually trained for recognizing certain objects, and here a horse and a zebra is not that different, really. And this is an example from a Belgian zoo. Some zebras decided to take a day off from the zoo. So an AV that does not recognize what it's seeing might cause a disengagement because it doesn't know how to react to it. Now, not classifying something correctly in most instances of an AV being trained not to run over things and not cause accidents is one thing, but it also comes into play at the higher levels of autonomy of where you need to actually understand what the behavioral model of a given road user is. So a bike reacts differently from a motorcycle, reacts differently from a car, which reacts differently from a pedestrian. So being able to anticipate the movement pattern of another road user becomes important in the planning aspect. So if you're not able to classify This might cause a disengagement again, and it has to be communicated up, and maybe a human has to say, oh, well, those are horses, here's new training, or a higher level training agent with more compute capability might retrain and send a new neural net weights and classifier information parameters so that the next time this car sees something, it knows what it is. Now, and then, talking about road conditions and weather conditions, and I want to take the example of potholes and snow. I'm from Canada, so the snow piece is half our life, and potholes is the other half that the snow leaves behind. So what we have in potholes, potholes are very evil when it comes to autonomous vehicles, because it creates two layers of problems. One, a pothole, in most senses, an obstacle for a vehicle in a vision system is something that's above the driving surface that you might hit. A pothole actually sits below the driving surface. And a pothole might look like a pothole, but it actually might be an oil stain, it might be a puddle, it could be an old pothole that somebody has filled, but the texture is different, so it still is recognized as a pothole. And this could cause various issues for the camera systems, detecting something that's not there, or detecting it wrongly. The other part of the difficulty that a pothole might create for an AV, as I mentioned in the mapped example, where you have a very clear corridor that you need to stick to drive, if a pothole is actually forming on that corridor where you're driving, you might have very high maintenance costs in terms of steering and suspension components, because the car is constantly going to hit that hole and have issues with you. So there you go into maybe updating the map such that if you have a fleet learning model, the fleet starts shifting out such that it has less impact on your driving and tries to maintain a different path through that zone so that the ride to the user is more enjoyable. And the weather aspect here, weather is one of the main culprits of the current systems having disengagements. So weather in terms of rain, fog, snow is a leading cause of disengagements in most AV vehicles nowadays. Another difficulty is optical illusions. And this is interesting because this is a system that we create to make human drivers better drivers. I mean, these are two examples of one, again, from an example from Canada in a school zone, trying to raise awareness of drivers to notice a child. It's a decal that's stuck to the asphalt, and at about 15 meters, so 40 feet or so, it looks like a child running after a ball. But as you drive up to it, at about 3 meters, it's actually distorted, and a camera system would not recognize it as a child. But you would have the condition where your radar and LiDAR might tell you there's nothing on the road, but your camera system is telling you there's a child there. So which one do you pick? How do you decide to move forward in that model? Again, likely cause of a disengagement. Same thing with the 3D painted pedestrian crossing model of creating these optical illusions that are meant for humans to be more aware when they're driving, but that can cause issues for AV camera systems. And we talked about how these events have to be communicated up into the cloud, and how they would need to be logged. But it's also, there's the reverse activity. So when your car did not recognize the zebras, you told them, I saw this, I didn't know what it was. And there's the updated weights and parameters for your network the next time when they see a zebra to recognize it. You have the over-the-air updates model of both your perception and potentially your map data coming in. And the map data can be used for events where you have construction, so reroutes and detours in the roads, so that needs to be updated. The location of certain landmarks could be updated. The perception piece, as we mentioned, the weights of training can be updated, the parameters in the classes can be updated. And as the roads change, you would have updates coming in. For OTA to really be useful, I mean, the main benefits are that you have the ability to modify the application and to increase safety and security level of the car. And then it also allows you to add improved features post-purchase, post-sell of the vehicle. But it has, very strict demands on the system. And some of them are that, the effect on the driver, on the vehicle itself has to be minimal. So you cannot have it such that the vehicle is down for a given period of time, a very long period of time during this update. The update not going through should not actually disable the vehicle, itself. It cannot render the car unusable. And the security is a very big aspect as well. Whatever you're using as an OTA channel, an OTA gate, cannot also be used to attack attack the data that's on the car or to steal the data that's on the car. And this has implications in terms of identity and private information, et cetera, that comes into play. And if we start looking at some of the data needs, and here I picked the three typical usual suspects, as I call them, the three typical sensor models that we have, modalities that we have in autonomous vehicles and ADAS and any vehicle system of the camera, LiDAR, and radar, using some generalizations on the amount of data that's generated per sensor. You're looking at, for cameras, about 700 to 6,000 megabits per second. And in a level 3 and above AV model, autonomous model, you have somewhere between 4 to 12 cameras. And not all of these cameras are at the same resolution. Your front and rear facing cameras might be all the way up to 8, 12 megapixels in future gens, but you have your parking camera sensors in the megapixel, 2 megapixel range. So it's a distribution. And with that distribution in mind, the typical bandwidth needed for this is about 300 to 6,000 megabytes per second that you're generating of bandwidth data that you're generating just from the cameras. LiDAR and radar are less costly in terms of data generation, but still we have a significant amount of potential LiDAR sensors going into cars and radar components going into cars. Even though radar right now has a low resolution and low bandwidth requirement, that's growing as well with high resolution millimeter wave radar components being deployed into cars. And you could have anywhere from 2 to 8 radar sensors in a typical vehicle, especially an AV vehicle. So if I take this and I generalize and actually reduce and compress a bit of the data that would be generated, we're looking at about 3 gigabytes per second of data generated that might need to be communicated. And this is actually a fairly drastic reduction based on using some of the sensor data, using the most reliable sensor data, et cetera. So it's definitely not the maximum amount that you could be communicating up. And in a typical disengagement model, you tend to have 30 seconds prior to the event recorded and communicated, and about 5 seconds post-event. So you're looking at a 35-second window of data logging that you would want to log and communicate and track for purposes of retraining and analyzing what happened in any disengagement event. So that 3 gigabytes per second plus 35 seconds, roughly at 100 gigabyte of data that you're collecting per event that needs to be uploaded. And then if I take this into the typical connectivity protocols that we have for vehicles available today, and I didn't touch on to 5G, and I'll get into that, but if I'm looking at the original V2V, V2X protocol of DSRC, 802.11.p, that throughput is about 3.4 megabytes per second of throughput that allows you. For 4G LTE, this is averaged out. This is not the max that the technology provides, but it's averaged out based on frame drop rates when you're traveling at 100, 130 kilometers an hour, what would happen, and your averaged out throughput that you would get. The assumption is around 10 megabytes per second for 4G LTE. And with Wi-Fi, again, assuming a certain distance to your router with physical barriers such as walls and doors in between, you're getting, with 802.11ac Wi-Fi, an average of 80 megabytes per second of throughput that you could have. Now, it's easy to, the example that I used for an update to a perception module, it's not a realistic thing. It's about 7 megabytes. It's related to the demo that we actually have at this show today in the technology showcase. It's mobile net plus single shot detection. And if you wanted to update all those weights to do an extra classification, that would be about 6.7 megabytes right now. So that is not a true network that could be used for an AV system. It's a simplified view. It's about 80%, 90% confidence in most classifications that it does in 80 classes. But it gives you an idea of what a 6.7 megabyte network, if that needed to be updated, if a portion of a network needed to be updated, that it really could be done with any of these protocols because it's only a couple seconds, less than a second usually of that update time for that. That's once you've figured out that it's a zebra, how to tell that it's a zebra next time. But getting the data about what you did not recognize, that scene that caused you a disengagement, that 100 gigabytes that we talked about in the previous slide, that is quite a larger challenge. Now, if you talk about DSRC becomes impossible, that's 8 hours of connectivity that you would need while maintaining a 3.4 megabytes per second throughput. That's not realistic. Even when we get into Wi-Fi, it's a good 20 minutes that you would have to upload this data in. So we're seeing that the time cost that some of those connectivity protocols have in terms of getting the data off onto the cloud to be looked at is going to be a significant area of challenge. Today, most of the test vehicles out there, when they park, somebody can pull their hard drives, somebody has a good Wi-Fi link to their garage for these, the Waymos and whatnot of the world, so that's not an issue right now. I also wanted to touch on a simple driver monitoring system. So DMS is understood. DMS doesn't really need connectivity, but it could be used for driver scoring and driver analysis. And it could be another simple application that you could use in this realm for autonomous systems, and that could benefit from connectivity. Here with DMS systems, of course, it's not just about the insurance rates and awareness of the driver. For an autonomous vehicle system, you end up getting into the situation where the DMS can be used to actually check if the driver is able to take over from the autonomous driver. So if the human driver is in a state to take over in a disengagement that is initiated by the autonomous driver. And that's, again, another area where it could be used for connectivity. So from main takeaways in this, as I mentioned, we don't see cloud services and connectivity as an important piece of, it is an important piece of an AV, but it's not an essential piece of the AV story. So you need the connectivity for the quality of service and to limit false positives and to make the technology more user-friendly and more adoptable. But it's not a critical piece because the vision processing at the edge, it is a timing critical and real-time system. It cannot be offloaded, but it can be augmented by what's available off-board, off the vehicles. And as we discussed the connectivity, time and cost, the protocols that are available, that connection, and how much data is offloaded for the systems is going to be a significant factor in these systems as they progress. Couple resources. I do recommend you to check out NXP's S32 automotive platform for both ADAS and AV systems. We do have some demos in the technology showcase, and we also are very big on automotive gateways. So whereas the cars are becoming servers on wheels, and secure and safe updates over the air, as well as a couple links into more in-depth analysis of the protocols, the bandwidth, and other topics around the cloud for autonomous driving. Thank you.
Thank you, Ali. I had a question about you had two 802.11 examples there where if you have a 100 gigabyte event and it gets uploaded, 8 hours and 21 minutes sounds like it's a huge difference, but if a car is parked in a garage and it's going to be sitting there for 10 to 12 hours, does it matter? Like how do I interpret the goodness or the badness of that?
In Wi-Fi, it probably won't matter. In Wi-Fi, that could be doable with the 20 minutes and with a good router connectivity, but you're thinking of an event where a condition where you actually have Wi-Fi in your garage, which might not be the case. So
if you're driving, for instance.
If you're driving, this might be updated. In an event where this is a robo-taxi that is actually on the road most of the time so that it recoups its costs, it might never get into the garage to actually do a Wi-Fi update. So we need to find ways of reducing the amount of data and still maintain its fidelity and its usefulness for the event analysis while finding protocols that actually work.
And a related question is, you had a tilde in front of the 100. So presumably all the information that's being uploaded some of it you might not need, some of it would be nice to have
Exactly.
as opposed to must have. Are there any standards for what needs to be recorded for a disengagement?
I think it's so new right now that anytime you have the government or lawyers getting involved, they're going to want as much as possible. So right now, I think the safe bet is to try to log it all. And since most of the vehicles that are out there are test vehicles, that's not an issue because you have the hard drives and you can pull the hard drives as is. But when these get deployed as actual vehicles for the masses to use, then you have the situation where you need to have the minimum that's defined by regulation to be uploaded, which doesn't have a number yet, as far
I'm
as I
also
know.
wondering about, like you think about airplanes that have a problem, they have black boxes that can be recovered. Is there any thought given in the automotive industry to replacing the need to push this across wirelessly to just recording it locally?
So that's the way it's being done right now, but again, that's a very large, I mean, you're collecting petabytes of data as you drive each day, in a sense, so that's a very large collection of data that you're keeping. So it will get to a point where you want to reduce the amount of storage that you have on the vehicle, if this is a mass-produced, massively available vehicle, and you need a way to offload that securely and not rely on it being in the car. Even in the airplane situation, when an event happens, finding that black box, finding the data and reconstructing data is not always trivial.
Yeah. Other questions from the audience? All right, Ali, thank you for your presentation. Oh, yes.
Could you please comment on 5G? You promised, but you
Oh,
forgot.
yes. Yeah, well, I had time, so sure, definitely I will. So 5G, in a sense that as it comes, even if it's about 10 times better than 4G, if it has 10x less latency and 10x better bandwidth, then it starts being equivalent to Wi-Fi. What I showed for the Wi-Fi numbers. So it's still going to be a significant amount of time, even with 5G, to offload 100 gigabytes of data off. So it might be in the 10 to 15 minutes range for each disengagement event that you still have to offload. And doing it on the road, I mean, 5G has different ways of communicating. If you're driving at 130 kilometers an hour, you're not going to have a single beam, very reliable high-speed link. So you're going to still have that maybe 100 megabyte per second, best case 200 megabyte per second link that might reduce your 100 gigabyte upload to something around 5-10 minutes range.
Thank you very much. I represent Verizon here. I have an additional question.
Sure.
If we had an infrastructure, if you look at those light poles, that is actually monitoring the environment and would give under 10 millisecond response to these vehicles from multispectral sensors, think about visible and IR combined. Would that change your partitioning and the way you described mapping and some of the algorithms that are running in the vehicle?
I don't think it would change the partitioning because that infrastructure would have to be available everywhere for it to affect the architecture of the AV system that's supposed to run autonomously with no reliance on the connectivity piece. So if it's a purely urban environment and this is, let's say, a mass transit bus with a given circuit, then maybe that architecture model might be different from what you have from a consumer-bought AV with an L4 level of autonomy that most of the time has to be able to maintain autonomy without having a reliance on connectivity. That's what I would see as a very quick analysis as an answer.
Or maybe extending the event horizon of the vehicle and thereby increasing safety.
Yes.
Do you agree with that?
Yes, that could be potential.
Thank you.
All right, thank you.
One more question.
Quick question on connectivity in general in terms of security as well. So if you were considering the system design in terms of having a connectivity module uploading data and probably downloading from the server and so on as well, would there be a choice in designing these systems to separate the connectivity piece from the critical navigation controls in the vehicle, or could it be that you might just have everything connected and there is a potential possibility that a insecure connection, like a bad connector or a bad actor, can take control of the car and all?
So, I mean, definitely for getting anything onto the vehicle, those are So that's definitely a separate system from what you would have driving your path planning, et cetera. You would not be linking directly your update into your decision-making process. And that was one of the main demands on an OTA type of update of you cannot have a failed update or any update actually create a critical situation that, that disables the car or creates an unsafe, unsecure event. It's one of the biggest areas of, research of making sure that even for simple things like key fobs, et cetera, that, that there's no attacks on a car, and this is a lot more critical than that. So definitely those systems are kept separate, they're isolated, and an update would have to go several checks and security checks once it's uploaded onto the vehicle to then make it into the active part of planning.
Thank you so much.
Thank you.
All right, let's thank Ali again for his presentation.
Thank you.